In this class, we will see how we can analyze recursive algorithms. In the last two lectures, we briefly took a look at how to design recursive algorithms and what are iterative algorithms. We did not complete our discussion on iterative algorithms. In yesterday's class, we only saw the relationship between recursive algorithms and iterative algorithms. When recursive algorithms are tail recursive, they become iterative algorithms. That is what we saw yesterday. But that is not much of a help in constructing iterative algorithms. We will take it up through a video lecture instead of a face-to-face lecture. In this way, I will prepare a video lecture and share it with you. We are given a problem. To solve the problem, we need to, one, design an algorithm, two, construct the algorithm correctly, and three, analyze the running time of the algorithm. A very important and powerful method for problem solving is recursive problem solving. We are given a problem with its input. We break the input into a smaller input and an element. We solve the problem for the smaller input and obtain the solution. Using the solution to the smaller input, we construct a solution for the given input. We use such words as one, deconstruct the input into a smaller input and an element. Two, recursively solve the problem with the smaller input, obtaining the subsolution. Three, construct the solution to the instance from the subsolution. Once we have an idea, constructing the algorithm was mostly straightforward. But we are also interested in the resources the algorithm takes to run. What is the cost of running the algorithm? That is what we mean by analysis of algorithms. In this lecture, we will see in particular how to analyze recursive algorithms. What is list recursion and what is tree recursion? We will illustrate list recursion and tree recursion. And also, how do we analyze list recursive algorithms and tree recursive algorithms? In this class, we will demonstrate or illustrate how to analyze a list recursive algorithm or tree recursive algorithm using a very simple method called unrolling. So, what are list recursive algorithms? What is tree recursive algorithms? How to analyze them using unrolling. Some examples we will discuss in the class. Other examples I will leave it to you for self-study. And finally, quickly take a look at what are asymptotic growth functions. Okay. Don't read all the contents of the slide. That is for your reading at leisure. This is a recap of what we saw yesterday. Given a list, say 5, 8, 3, 9, head is the first element of the list. So head of 5, 8, 3, 9 is 5. If you remove the head element from the list, the resulting list is called tail. So tail of 5, 8, 3, 9 is 8, 3, 9. So this is the tail and this is the head. If you are using a Python list and you are given a list U, then I said U at 0 is equivalent to head of U, U at 1 to the end is the tail of U in Python. I will also use an operator I called prepend. Five prepended to the list 8, 3, 9 gives us 5, 8, 3, 9. The word prepend is something like append. Appending an element means adding it to the end of the list. Prepending an element means adding it to the front of the at the start of the list. Okay. So suppose we have something like this. I am using colon as a prepend operator. It is not available in Python programming language, just for our convenience. So 5 prepend, 8 prepend, 3 prepend, 9 prepend, empty list. The prepend operator associate from right to left. So 9 prepended to empty list is list consisting of 9. Then 3 prepended to list consisting of 9 is 3, 9 list. 8 prepended to 3, 9 is 8, 3, 9 list. 5 prepended to 8, 3, 9 is 5, 8, 3, 9. Therefore, the list consisting of 5, 8, 3, 9 is only a shorthand for 5 prepend, 8 prepend, 3 prepend, 9 prepend empty list. Okay. Also, look at this complementary nature. 5 prepend 8, 3, 9. If you take the head, it is simply 5. If you take the tail, it is simply 8, 3, 9. So I said head and tail are complementary operations to prepend. This is just a very brief introduction to list. In Python, since we don't have prepend, suppose you want to prepend 8, 3, 9. How do you do that in Python? Python, you have to do it as 5, make it a list, plus 8, 3, 9. It is not prepend, it is only a concat. Concat concatenates two lists. Items of the second list are added at the end of the first list. So Python does not have prepend, but we can simulate prepend using this without worrying about the time taken or cost. Okay, now for list insertion. Suppose we are given a list, say 6, 4, 7. It is sorted. And we want to insert a new element 6. After adding the new element to the given list, the new list, the resulting new list should also be sorted. This is the resulting new list. So 6 is added to the list 4, 5, 7, and we want to get the list 4, 5, 6, 7. This is also sorted. This operation I call ordered insertion. Insert a new element, an element into a sorted list so that the resulting new list is also sorted. Let me call the operation I. I takes two arguments. 6 is the element. So let U be the element, V be the list. This is the first argument is an element, the second argument is a list. How can we do it recursively? Divide the list into the head and tail. 4 is the head, 5, 7 is the tail. Okay. If suppose the given element is 2, to do ordered insertion of 2 in 4, 5, 7, what do we do? Oh, 2 is already, yeah, that's it. 2 is prepend. 2 is already less than 4. Therefore, there is nothing more to do. The resulting list is 2, 4, 5, 7. Oh, that gives us an idea. If U is less than the head of V, what should we do? U should be prepended to V. That is the result. Let me also give another thing. Suppose I want to do insert 6 to an empty list. What is the result? 6 again. So I have one other case. If V is equal to empty, this is case 1, this is case 2, then the result is simply U. All right. Oh, let me put this way. Otherwise, 6 is not less than 4. So divide or break the list into head and tail. The problem of insert 6 into 4, 5, 7 can now be reduced to insert 6 into 5, 7. 4, 5, 7 is the given input. 5, 7 is the smaller input. We have already seen we have to ensure in a recursive call, the input size should be strictly less than the input size to the original call. The input size to the original call is, okay, the input is 4, 5, 7, therefore the input size is 3. Let us measure the input size in terms of the number of elements of the list, the length of the list. Whereas the input size to the recursive call is 2. After we have inserted 6 into 5, 7, all that we need to do is prepend 4. After we have inserted 6 into 5, 7, what will we get? We will get this. 5, 6, 7. Look at this. To 5, 6, 7, what should we do with the head? Just prepend. And therefore, I can write the recursive case as, okay, I had to insert U into what? The tail of V. There is a sub-solution. Tail of V is the sub-problem or sub-instance or smaller input. And this is the solution. To this solution, to construct the solution to the problem, all I have to do is,
head of V.
Yeah. Head of V. That's it. All right. The first illustration, okay, insert 6 to the list consisting of 7. Oh, fortunately, 6 is less than 7. Therefore, the recursion stops. 6 is prepended, we get 6, 7. Then 5 is prepended, we get 5, 6, 7. Then 4 is prepended, we get 5, 6, 7. In this case, ordered insert 9 to 4, 5, 7. Then insert 9 to 5, 7. Then insert 9 to 7. Then insert 9 to empty list. Inserting 9 to empty list is simply 9. Then prepend 7, prepend 5, prepend 4. Okay. That's all. That's all. These are base cases. We said every recursive algorithm should have at least one base case. It can have two base cases, three base cases, and so on. In this problem, we have two base cases, and this is the recursion step. Now we can write the algorithm. Algorithm ordered insert U is an element, V is a list. Input a sorted list V and target U to be inserted. Output U, oh no, not okay. This is also okay. U prepended to V, it has to be sorted. Or if you want to be very clear, a sorted list consisting of all the elements of U and all the elements of V. The two base cases are if V is equal to empty list, then return a singleton list consisting of only U. The first case. Okay. If U is less than or equal to the head of V, all right, we have reached the right position for U, and therefore all that we have to do is prepend U to V and return it. That's the result. These two are the base cases. If the control reaches this point, that means U less than or equal to head of V is false. V is equal to empty list also false. Therefore, negation of U less than or equal to head of V is head of V is less than U. Since head of V is less than U, head of V should become the first item, first element. Therefore, it should be prepended. What is the recursive call? Ordered insert. The arguments, the inputs are U comma V. Here the inputs are U comma tail of V. And look at that. Tail of V. Size is strictly smaller than size of V. One less than that. In this class, we are interested so we started with the design idea for ordered insert. Then we constructed the algorithm. Once we have the design idea, construction of the algorithm is almost suggesting itself. There isn't much to do. So the algorithm is correct by construction. But we are also interested in the running time of the algorithm. What I have not told you up till now is how do we measure the running time? I said running time is not measured using a wall clock. It is not measured using wall clock. Then it is measured using what? I will tell you. In every algorithm, there will be at least one operation that is most frequently executed. I will call that the basic operation of the algorithm. Okay. The basic operation may be comparison, or the basic operation may be prepending, or the basic operation may be swap, or the basic operation may be an assignment, and so on. Suppose I say the basic operation in ordered insert is a comparison. Comparison of two items is the basic operation. Then running time of the algorithm is only how many times totally the basic operation is executed. I will call the running time t if the input size is n as t of n. Then for the recursive call, the running time is t of, if the input size to the call is n, what is the input size to the recursive call?
-1.
N minus 1, because tail of V is just 1 less than V. The algorithm itself, how many comparisons does it do? Just one comparison. Here. Every time the algorithm is executed, this one comparison has to be done. It is also possible, okay, the basic operation is both comparison and prepend is also okay. But if I consider only comparison as the only operation, in addition to T of n, what is the running time of call T of n? The running time of recursive call T of n minus 1 plus 1. The 1 is the number of comparisons. One call of the algorithm does only one comparison. Plus the time taken by the recursive call. The time taken by the recursive call is T of n minus 1. That is what we have written here. If n is greater than 0, T of n is equal to T of n minus 1 plus 1. Suppose n is equal to 0, T of 0. That is, V is an empty list. When V is an empty list, there is no comparison done. Therefore, if you want, we can put 0 also. But at least we are doing one, let's say, V is equal to empty list is a comparison. If that is counted as a comparison, then we are doing one comparison. This we call a recurrence relation. We are defining T of n. The name which is defined occurs on the left side, T. The same T occurs on the right side also. So T is defined in terms of itself. This T of n minus 1 is a self-reference. On the left side, you have the defined name. On the right side, you have a reference to that name. Therefore, it is a recurrence or a recursive definition. The recurrence relation does not give us an idea about the total number of comparisons the algorithm makes. So what we want to do is somehow transform the recurrence relation to get an idea about T of n. What is the total number of comparisons? A recurrence relation in this form is said to be closed form. What we want to do is, we want to solve it. T of n is equal to 1 plus T of n minus 1. This T of n minus 1 can be written as 1 plus T of n minus 2. 1 plus 1 is equal to 2, and then we have T of n minus 2. This can be, T of n minus 2 can be written as 1 plus T of n minus 3. Do the simplification, 2 plus 1 is equal to 3, we get 3 plus T of n minus 3, and so on. After n times doing the same thing, we will get n plus T of 0. T of 0 is equal to whatever, 1, n plus 1, and I will say, ignore this 1, and what we get is n. When we are ignoring certain terms, whatever we get is called asymptotic growth. Asymptotic growth. When n is equal to 10, 10 plus 1, 1 matters. When n is equal to 100, in 100 plus 1, 1 does not matter so much. When n becomes 1000, 1 is almost negligible. When n becomes million, billion, 1 does not matter at all. And that is what we mean by asymptotic growth. When n grows to a very large value, some of the other terms can be ignored, can be discarded comfortably. And what we get is called this big O of n is called asymptotic growth. We also say it is a linear growth. As n increases, the input size increases, the running time increases linearly. So we say we started with T of n is equal to 1 plus T of n minus 1. This is a closed form. And we finally obtained T of n is equal to big O of n. This is called, the first one is, I think I'm wrong. This is which is closed, which is open, I'm not sure. Okay, this is open. open form, or we also say it is a solution of the recurrence relation T of n is equal to 1 plus T of n minus 1. It is a field in itself. In discrete mathematics, people study how to solve recurrence relations. But we will not go into the detail. The technique or the method that we have followed to solve the recurrence relation is called unrolling. Unroll. T of n is written as 1 plus T of n minus 1. Unrolling once. T of n minus 1 is written as 1 plus T of n minus 2, unrolling the second time. T of n minus 2 is unrolled into 1 plus T of n minus 3. After a succession of unrolling steps, we have solved the equation. And therefore, the running time of ordered insertion is linear, big O of n. Now that we have, homework should be, I will come to that later. Now that we have a nice ordered insert algorithm, let us use it for doing something useful. I call that insertion sort. Insertion sort is given a list sort V. V is a list. S for sort. Sort 6, 5, 7, 4. I will divide the list into the head and tail. Head is 6, tail is 574. So I will say sort 574. That is a sub-problem. This is a problem. This is a sub-problem or sub-instance. The input size is 4. Here the input size is 3 because there is a tail. After we have solved it, we will come here. After 5, 7, 4 is sorted by insertion sort, we will get 4, 5, 7. Now what should we do with the head? The head 6 has to be inserted in the appropriate place in the sorted list so that the resulting list is also sorted. What is this operation? Insert 6.
Ordered insert, sir.
Ordered insert. So insert 6 in an ordered insert 6 into 4, 5, 7 will give us 4, 5, 6, 7. All right. So we can trace the recursive process. Sort 5, 7, 4 will become sort 7, 4 and ordered insert 5 into that. That sort 7, 4 will become sort 4 and ordered insert 7. Sort 4 will become sort empty list and ordered insert 4. And then we are unwinding or the return journey. Ordered insert 4 into empty list will be 4. Ordered insert 7 into 4, 4, 7. Ordered insert 5 into 4, 7, 4, 5, 7. Ordered insert 6 into 4, 5, 7, 4, 5, 6, 7. So the idea, we have the idea, the design idea for the algorithm. Take a minute and write the algorithm before we go to the next slide. What is the base case? What is the recursion step? What is the base case? Can anyone try?
Sir, if the list becomes empty, we have to return the empty list, sir. Like,
okay. If this is empty, then you have to return empty list. That's the base case. Very good.
yes, sir.
Okay. How about the recursion step?
Return ordered insert of the head, comma, the sort of tail.
We are given V. We break it into tail of V. So sort tail of V. And then all you have to do is ordered insert the head of V. Right?
Yes,
That's
sir.
what we did. Here is the algorithm. Algorithm insertion sort V. Input is a list V. Output is sorted V. It is not the same list. The output list is distinct from the input list. I will come to that in a moment. So the base case is V is equal to empty list, then return empty list. If the input is empty list, output is empty list. The recursion step is ordered insert V The input now is tail V. The input size is strictly less than the input size to the call. Okay. And how do we construct the solution? Ordered insert the head of V. Let me complete the analysis of the running time. Then I have some very important comments to pass. What is the running time of the call T of n? What is the running time of the recursive call T of n minus 1? Because if the size of V is n, the size of the input to the recursive call is just 1 less. So it is T of n minus 1. Okay. Now, what is the important operation? The basic operation done here, ordered insert. There may be a comparison operation, head is an operation, tail is an operation, but those are very trivial operations. Head and tail are trivial operations. Okay, they are done in constant time. Ordered insert is the costliest operation. One call of insertion sort does how many calls of ordered insert? Just one ordered insertion, right? But what is the running time of ordered insert? What is the running time of ordered insert?
N.
Big O of n. If the input size is n for ordered insert, the running time is big O of n. Here, what is the input size to ordered insert? N minus 1. If I consider the result of insertion sort of tail of V, the input size is n minus 1 for insertion sort, the output size will also be n minus 1. So how many comparisons will ordered insert take? N minus 1 comparisons. If you put n, it does not make much difference. In asymptotic growth, such things disappear. It is very important. You should, okay, maybe I made a mistake in saying that the basic operation is ordered insert. The basic operation is still comparison. The running time of the algorithm is T of n. The running time of call. The running time of the recursive call is T of n minus 1. The running time of ordered insert is n minus 1. Therefore, the running time, the recurrence relation is T of n is equal to 1 constant time if n is equal to 0. V is an empty list. The input is an empty list. Otherwise, if n is greater than 0, the running time is T of n minus 1 plus n minus 1. Now, we have a very simple method for solving recurrence relations. We call that unrolling. Can you unroll it? T of n is equal to n minus 1 plus T of n minus 1. Unroll one time. Okay. Then unroll T of n minus 1. You will get T of n minus 2 plus T of n minus 2. Unroll T of n minus 2. We will get n minus 3 plus T of n minus 3 and so on. Eventually, we will reach 1 plus T of 0. So, this is n minus 1 plus n minus 2 plus n minus 3 plus 1. That is n minus 1 times n by 2 plus T of 0 is constant. If we expand, it is n squared by 2 minus n by 2 plus 1. My argument is when n becomes very large, 1000, million, 1 million, this 1 can be ignored. This n by 2 can also be ignored. Okay. I call them lower order terms. Ignore lower order terms. Also ignore this factor, constant factor. We are left with n squared. So we say that the running time of ordered, the insertion sort is big O of n squared. Right? If it is 10, okay, 1, it is 1. It is 10, it is 100 comparisons. If it is 100, it is 10,000 comparisons and so on. As the input size increases, the running time increases quadratically. Let me take a stop here and ask you. Have you implemented insertion sort before? You have done that. You have done in exercise 1 also, right? The
Yes,
session.
Yes, sir.
All right. Generally, do you do insertion sort using a list or using an array?
array, sir.
Using an array. How do you compare the understandability or the clarity of insertion sort using list versus insertion sort using array? Just 2 lines or maybe 3 lines insertion sort. Ordered insert itself is another 3 lines. So ordered insert 3 lines, insertion sort 2 lines, and there is no need for keeping track of any indices 0, I, j, n minus 1, n. How do you evaluate? How do you compare insertion sort implemented using lists and insertion sort implemented using arrays? Which one appears to you more readable, I mean, readily understandable and clear? Response.
List, sir.
Using list or using array?
Using list, sir.
Using list.
Sir.
Okay. Remember, your Python list is both a list and an array. For example, in Python, this will be this head of B ordered would be written as V at 0, okay, and then this is ordered insert U into V at 1 to end. There is no prepend operation in Python, so what would you do? V at 0 is an element. The result of ordered insert is a list. Therefore, you have to make this into a list and then concat. That's how you will write in Python. Similarly here. Okay. The homework is, if you have not implemented, you would have implement insertion sort using an array and compare it with insertion sort using list. When you implement insertion sort using an array, you have to analyze the running time. We have not yet discussed how to analyze the running time of an iterative algorithm. Therefore, running analysis you can keep pending, but homework is implement insertion sort using array. Okay, let's go on. Merge. Operation merge takes 2 sorted lists as arguments and results in a sorted list of all the items in the argument list. We will denote merge by the operator plus plus. It is not a standard notation. Python or no programming language uses plus plus as an operator for merge. In this class, for convenience, I am using this. For example, 2, 3, 8, 9 is a sorted list. 1, 4, 5, 7 is a sorted list. When you merge them, you will get the merge of the two lists is a new list consisting of all the items of both the lists in the sorted order. So it should be 1, 2, 3, 4, 5, 7, 8, 9. All right. Can we implement merge using ordered insert? We can insert 2 into, do ordered insert of 2 into 1, 4, 5, 7. Then ordered insert 3 into that result, ordered insert 8 into that result, ordered insert 9 into that result. And that's what I have done here. Repeated order insert from the start. 2, 3, 8, 9 plus plus merge 1, 4, 5, 7 is simply ordered insert 2 into 1, 4, 5, 7. What will be the result? 1, 2, 4, 5, 7. It is ordered insert. We have already implemented. To that, you have to merge 3, 8, 9. And this can be written as ordered insert. Take the head of the list. Ordered insertion of 3 into 1, 2, 4, 5. We'll get 1, 2, 3. 3 is put here. To that, you have to merge 8, 9 and so on. This is one algorithm. What is the running time of the algorithm? Can anyone guess? To do one order, okay, you can always assume the worst case. All right. Suppose there are n items here and n items here also, equal number of items. What is the running time of merge if merge is implemented using repeated order insert from the start?
O of n square.
Remember, to insert 2, I start from 1, 4, 5, 7. To insert 3, I again start from 1, 2, 4, 5, 7. To insert 8, I start from 1, 2, 3, 5, 7, 8. To do one insertion, one ordered insert takes n, big O of n. It's okay to write it as n. To insert, to do ordered insertion of one item. Like that, how many items need to be, how many ordered insertion we need to do? N items. Therefore, this is n squared. Can you think of a better, more efficient method? For example, after you have inserted 1 into 1, 4, 5, 7 here, you have to insert 3. In order to insert 3, you don't need to start all the way from 1. You can continue sweeping, continue scanning this list from wherever you stopped. And therefore, can 3 be inserted here? Oh yes, we can insert it. Then can 8 be inserted here? No. Then you continue. 4, 5, 7. Oh, we come here. Can 8 be inserted here? Yes, 8 can be inserted here. Then can 9 be inserted here? Yes, 9 can be inserted here. Okay. So what is the basic idea? Instead of scanning the list every time from the start, continue scanning from wherever you left. And that is the idea here. Ordered insert in a single sweep. Okay. What should we do? Compare, we want to insert the items 2, 3, 8, 9 into the sorted list 1, 4, 5, 7. Both are sorted. The idea which I have stated would effectively become compare 2 and 1. In the new list, in the merged list, which item will come first, 2 or 1? 1. You compare the head of U, suppose this is U, this is V. Compare the head of U with the head of V. Whichever is smaller will be the head of the new list. And then you remove this. Now the problem becomes merging 2, 3, 8, 9, merge 4 comma 5 comma 7. So we have reduced the size of the problem. If the size is n, where n is the sum of the lengths of len of u plus len of v. We have reduced the problem to n minus 1 because we removed the head. If we trace the process, compare 2 and 4, which is smaller? 2 is smaller, therefore 2 will become the head of the new merged list. Remove that, we have reduced the problem to 3, 8, 9, merge 4, 5, 7. Complete the trace and you will get something like this. So we have the design idea. Merges two sorted lists. Look here. For example, in this case, 8, 9 merge empty list. If one of the lists is empty, the result is simply 8, 9. So if this is U, this is V. If V is empty, the result is U. If U is empty, then the result will be V. That's also possible. And therefore, if V is empty, the output is U. If the input U is empty, then the output is V. Otherwise, what should we do? Compare the head of U with the head of V. Whichever is smaller, head of U is smaller, and therefore that will become the head of the new list. We have deconstructed. Since remove U and remove the head of U, we will be left with the tail of U. Okay. So the sub-problem is tail of U, merge V. Merge V. Otherwise, the role of U and V will be changed. Head of V, prepend it to the sub-problem is U merge with tail of V. That's it. This is almost a solution. We can express the algorithm in this way. Algorithm merge U comma V. Input U and V are sorted lists of items. This is important. That's a precondition. If U or V is not sorted, this algorithm, the output will not satisfy the input-output relation. Only if the precondition is satisfied, the algorithm will ensure the postcondition. If the precondition is not satisfied, the algorithm has no guarantee. Okay. Output is a sorted list of all items in U and V. There are two base cases. If U is equal to empty, then return V. If V is equal to empty, then return U. And this is the recursion step. If head of U is less than head of V, then the sub-problem is merge tail of U and V. We have removed the head of U, that should be prepended to the new list. Otherwise, change the roles of U and V. What is the running time? T of n is equal to 1 if n is equal to 0. T of n otherwise T of n minus 1 plus 1. How do we say that? Look at this example. I think I have to stop. With this example, we'll stop. 153. T of n is the running time for 2, 3, 8, 9, merge 1, 4, 5, 7. In the sub-problem, the input size is n minus 1. If it takes T of n time units for merging two lists whose total length is n, the running time for merging the sub-problems is T of n minus 1. Okay. Plus constant amount of work we may have to prepend. Or from the algorithm also we can argue here T of n. Let me ask a simple question. How many recursive calls this algorithm makes? How many recursive calls algorithm merge makes?
In one
So
iteration, just one, sir.
When merge is called, does it make one recursive call or two recursive calls?
In one iteration, it just calls one merge, sir.
There is no iteration here. In one call to merge makes how many recursive calls? One or two or more?
One, sir.
One. Oh, but there are two. Here is a merge. Here is a merge. Are there not two recursive calls?
But sir, the both cannot be called at the same time. Only one will be called, right? Because both are like conflicting cases. So
Yeah. It's a if else. Therefore, it's a case analysis. If the condition is true, this merge will be called. If the condition is false, this merge will be called. Always one merge. And therefore, this is still a list recursion or linear recursion. If one call makes just one recursive call, we call this list recursion or linear recursion. All right. So other than T of, so therefore this is T of n minus 1, plus there is just one comparison. Therefore, the running time is 1 plus T of n minus 1. When you solve it, we have already solved this recurrence relation. This is big O of n. Compare this against the repeated ordered insert. If you use repeated ordered insert, the running time was big O of n squared. But the merge, we have done it more efficiently and takes time, which is only big O of n. Homework and for tomorrow's work. Look at this algorithm. If you have a merge, it is so useful, so powerful. We are just one step short of a very interesting sorting algorithm called merge sort. Algorithm merge sort, just 1 minute. B 0 to n is a list of comparable items. Output is a sorted list of items in V. Okay. What is the length of V? Let it be n. The base case is if the input is a empty list, the output is an empty list. Input is an empty list. After sorting, the output also is an empty list. If the input is a singleton, there is one item in the list, the output is also the same. So therefore, we say if n is equal to 0 or n is equal to 1, then output V is the same as input V. Base case. Otherwise, roughly take 1/2 of the length of the list. M becomes n by 2. Then what we have to do is take the first m items 0, 1, 2, m minus 1 and the remaining items m plus 1 and so on n minus 1. Roughly half. This is 1/2. This is another half. This size is m. This size is m or m plus 1, whatever. So do merge sort of the first half. This is sorted. Do the merge sort of the second half. This is also sorted. If we have two sorted lists, we can merge them into a new sorted list using merge. That's a very simple algorithm.